All right. So let's continue with the simple problems that we have been addressing with Ginsburg-Landau. And in the last class, we had, I think, started this little parts effect. All right, so how do we understand this little parts effect? I have given you the qualitative physical explanation. However, of course, we need to work it out better in this class. So before I start with the derivation, in the very beginning of our course, when we were doing the phenomenological survey, we have done the flux quantization. So just to remind you, what we have done is, since in a superconductor, the Cooper pair, the charge carrying entities, do not undergo any scattering, the wave function is rigid. The phase of the wave function is rigid, which means that if you start from here and come back here, you will get the same phase, or at most you can get a phase change of 2 pi, because the phase change of 2 pi is the same as 0, a multiple of 2 pi. So using this, what we had derived is the flux quantization condition, through which we showed that we specifically showed that the vortices will carry a flux of 1 flux quantum. This n is normally 1, so it will be h by 2e. And more generally, what we showed is that if you have a superconductor with a hole and you apply a magnetic field, the flux inside this enclosed superconducting contour has to be an integral multiple of a flux quantum. Okay, so what we, so this, if you recall, the steps that led to this derivation was the following. We had this equation, which is the general equation from which we derive the flux quantization condition, by assuming that Js is 0. So in the situation where I have Js 0, then of course I am left only with the vector potential, and I'll have this flux, which will be an integral multiple of 1 flux quantum. In general, what would happen is that this quantity as a whole has to satisfy the quantization condition of this being a multiple of 2 pi n. So therefore, if I just rewrite this expression, then I can write it in the following fashion. The total flux that is given by A dot ds So this is the integral of A dot ds, which is giving me the total flux in that contour. Then this is the contribution from the current, and this will be equal to phi naught, which is h by 2e into n. So I write that as phi naught n. Okay. So in the presence of current, of course, what will satisfy the quantization condition is not the flux as such. It is this whole quantity. And this is what is called a fluxoid. A fluxoid is actually the contribution to the phase from the flux plus the contribution to the phase that comes from the supercurrent. Okay. So now I know that as usual, Js is Ns E star Vs, and then if I replace, then I will get phi plus mc by E. Is that correct? Yeah, I think so. I think this is correct. Integral of Vs ds, and this will be n phi naught. Good. Okay. So that means that this. Now, if I have remembered the geometry that we were considering is actually a circular ring like this. So for, let's say, a circular contour like this, which is running along the, let's say, circumference of this tube, then Vs by symmetry will be a constant, and this will be 2 pi r, if r is the diameter of the radius of the tube. So therefore, then from symmetry, I will have here is actually I'm using CGS, so somewhere I wrote something wrong. There should be a C here. Okay. That is a small change, and then this will become r is the radius of this quartz fiber on which I have coated the superconductor. And I will have here phi by phi naught. N is an integer, n is actually the nearest integer to phi by phi naught. Alright, so this is the first part of the derivation. You know that phi is nothing but the magnetic field that I am applying into the area. If you want pi r square. So therefore, this immediately tells you that the velocity of the superelectron will have a periodic variation. Now, the next thing is to connect the velocity of the superelectron with Tc. Now, for this connection, we need to go back to this problem of critical current in the critical current in a thin wire that we have solved before. Let's say was it this one? I don't recall which one it was. No, this is the Josephson junction. So it must be after this. No, sorry. Where did that go? Oh, this is for before. Ah, okay. It was here. Okay, that is good. So we know that this was the relation between Js and the superfluid velocity, but here we have a better relation. Yes, this is the relation that I was looking for. We have derived this relation in, I think, the last class or the class before. And this is how the amplitude of the Ginzburg-Landau order parameter varies with Vs. So now, this is the expression that I will substitute in my little parts derivation. So therefore, what I will use is the expression psi mod square, because here I can, this though little and parts are done by coating a cylinder, you could have in principle taken a ring. Here the symmetry of the problem doesn't attribute any special effect from the z direction continuity, because the current is confined, because you are applying the magnetic field along the cylinder, the current is going azimuthally, so therefore the z direction has no significance. All right, so this and now we know from substitution that this will become twice xi m Vs by h cross whole square. I have just replaced the expression of, I have replaced alpha with using the relation between alpha and xi. Alright, this is what I get. Now, Tc, at Tc, psi mod squared has to go to 0. So therefore, the condition for Tc will be that 1 by, sorry, 1 by xi squared is equal to this quantity over here, 2m Vs square by h cross, and then Vs square. Now I can replace it. I can replace this whole thing, and what I will get is 1 by r square. I use the expression from Vs from here. I substitute that. And I will get 1 minus r square n minus phi by phi naught whole square. Okay. Now there is a relation that I have not derived yet, which is, so I know how the Ginzburg-Landau coherence length will vary with magnetic field, but if I really want Tc, then what I need to know is, now I need to substitute and find the relation for Tc here. So what I will do is, let me check what I will do. Okay, there is something I haven't derived before. I haven't derived something before, which is, I haven't derived the temperature dependence of xi, which I will have to use here. So let me just check whether we need that or we can. Actually, what I will do is, this expression is not, okay, this I think is a simple enough expression. I will leave it for assignment problem. So today I will be circulating the assignment. So as the assignment problem, it's fairly straightforward. Try to derive that the Ginzburg-Landau coherence length is proportional to Ginzburg-Landau coherence length at t equal to 0 into 1 by t to the power half. Now, is anyone getting any clue of how that might be coming? Okay. If you are not getting a clue of how it might be coming, I will just leave it for you to derive it. It's very simple. It's a very simple derivation, but let me not give you all the hint right away. Okay, so now using this expression, you can see that this variation of with magnetic field of psi will immediately translate into a periodic variation of Tc here, because here the only thing that you can vary is Tc. Psi naught is something that is that cannot depend on magnetic field because it is by definition in zero field. So with this expression, you can, it's very easy to invert this expression, which I will not do, and you will see quite trivially that delta Tc by Tc, the fractional change of Tc, will be 0.55 psi naught square by r square into 5 by phi naught whole square. And this is precisely the reason why you have the periodic variation, because you have first n, remember, is not a constant, it's the nearest integer. And it's the nearest integer because if, for example, your magnetic field is large, so suppose this quantity here is 5, and you keep n at 1, then it will be a valid solution but much higher in energy. That will not be the lowest energy solution. Go back to the Ginzburg-Landau free energy, and that's very easy for you to convince yourself. So therefore, since this is the nearest integer, you have the delta Tc is the suppression. So this is the negative delta Tc. It's how much Tc is suppressed. When you have this which is integer, then this quantity is 0. So there is delta Tc is 0, there is no suppression of Tc. Then as you increase the magnetic field from the integral value, this becomes a positive quantity, and therefore you start having a suppression of Tc. This suppression is maximum in between two integers. So for example, at 2.5, at 3.5, 1.5, and so on. And it sort of vanishes, the suppression vanishes at the integral values. That is how you get this periodic variation. All right. So now we'll take another simple problem. Is there any question? Let me take that first.
Hello. Hello.
Hello, yeah, Gorachand, go ahead.
Ah, so when you derive the expression for Vs from symmetry argument, so we take for the integral over ds, we take the unit length, right? I mean 2 pi r into unit length L.
2 pi, we can take 2 pi r. So just a minute, let me go to the relevant portion. Yes,
Yes, yes.
So
Huh.
this quantity, we take it as Vs into 2 pi r. So
Okay, okay. I mean, huh. So ds is the surface area of this
no, 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 no,
wire,
no, no, sorry,
whatever
sorry.
we
ds,
considering. I mean,
okay. I think ds is not surface area. ds is the unit length. If you want, did I confuse you? Maybe I should write as dl then. So
okay, okay, sir.
if I have a ring like this, dl is this element here. This unit vector, this elemental vector here.
Yes, sir. I confused with ds with surface area. Okay, okay. Thank
Okay,
you. Yes.
all right. Okay, yeah, actually I have always used DL. I don't know why I use DS here. I think one should not use DS. Okay. Any other question? Okay. If not, then let us take up one more simple problem before we choose to take up more complicated problems. Okay, so the next simple problem that we will take is oops, sorry. Is the critical field of a thin film with the magnetic field which is applied parallel to the film plane. Okay, now this I have told you before in the context of the group which is doing the video project on Messervy-Tedrow. Who is that? Can you, who are doing the project on spin polarization measurement using Messervy-Tedrow and point contact and reflection?
Sir, I am
Shumon. And who else?
Jaideep.
Jaideep. Okay. So remember, this is what I have told you before, that if you apply, sorry, I'm drawing it quite badly. Okay, if I have a thin film of a superconductor like this, and if I apply a magnetic field which is exactly parallel to the film plane, then superconductivity will persist up to a field which is much higher than the critical field, and actually much higher than the critical field. So, as I have mentioned to you before, if we, for let's say aluminum, which has a critical field about 0.1 Tesla, 1 kilohertz state, if you apply the field, this is when you apply the magnetic field perpendicular to the film plane. But if you apply the magnetic field parallel to the film plane, then your superconductivity will persist in the same aluminum film up to, let's say, 4 or 5 Tesla. So it increases by a factor of almost 100, so 70 or 80. So it's an enormous increase. So we will see now in Ginzwald now whether we can at least show that it can increase. And then the microscopic mechanism of increase is of course different. That I have explained to you at that time. That you will not be able to directly get from Ginzburg-Landau. But this anomalous increase, whether it is justified within Ginzburg-Landau. Okay, remember now there is an advantage when I am doing the critical field. At the critical field, superconductivity is almost destroyed. And if superconductivity is almost destroyed, that means that, so close to HC, psi mod square is very small. Actually, it is tending towards zero, but it's not maybe completely zero, but it's very small. So psi mod square small means that ns is small, and if ns is small, that means that lambda is large. Now I am dealing with a thin film. I am dealing with a thin film here, which is much smaller than the penetration depth, even at t equal to, at h equal to 0, and therefore close to the critical field, this penetration depth is enormously large compared to d. D is the film thickness. So if d is so small compared to lambda, you know that the magnetic field decays exponentially over a characteristic length lambda, and that means that the magnetic field will hardly decay. So I don't need to consider really the fact that inside the superconductor the magnetic field is smaller than what I have applied. I can just pretend that they are almost the same. That helps me a lot, because how does that help me? Then inside the superconductor I can calculate the free energy with the vector potential A, which I will take as a y into z unit vector if this axis is z, yes. And so let me define the coordinate. This axis is x and this axis is z. And this axis is y. So the film is in the YZ plane. Okay. So this can be sorry, this is not A, this is H. I can take simply this as my vector potential. So it is very easy to see that if I do a curl of A, I will get, sorry, is that, sorry, I am making a mistake here. I'm making a very bad mistake here. Excuse me. Very sorry. This is A. If I take curl of A, then I will get H, which will be in the Z direction. Take a few moments to convince yourself that what I have written is correct. All right. So AY actually what I am, rather the vector potential A that I am taking here, you can also convince yourself that this is actually in the London gauge. Okay. So let me check a little bit more. Okay, so if I am in the London gauge, here I am in the London gauge, you know that in the London gauge, Js is proportional to A. And you put the constants correctly, you will get Vs, which will be given by this. Actually, for consistency, let me just use E star here also. E star is twice only. All right. So here I have just used Js to be Ns, E star Vs, and then I have used the prefactors, which I don't recall right now correctly. Okay. So now what I need to do is to find out from Ginzburg-Landau theory, I have to minimize the free energy and find out psi mod square. So this is what I need to find out by minimizing the free energy for a magnetic field which is large, which is close to Hc. Okay? Anywhere where you are not following the thread of argument, just interrupt me. Now, remember that so far what we have been using is the Helmholtz free energy. So the free energy density F that we calculated is the Helmholtz free energy. And this is the appropriate free energy when B is constant. But I want to find the critical field now. So when I want to find the critical field, I have to get the free energy where H is constant. Now there is a slight difference between these two. Can anyone tell me what the difference is? You have a StatMech exam tomorrow, is that right? Is that what some of you told me or you had in the last week?
So we had in the last week.
Okay, so then you should be on the top of this. If B is constant, I use the Helmholtz free energy. What do I use if H is constant? Let me then go back to a simple question. If you have temperature and volume constant, which free energy do you minimize?
Gibbs free energy.
Okay. So here when H is constant, which free energy will I have to use? I
Yeah,
have
it's
to
same the Gibbs free energy because magnetization and magnetic field are there.
exactly. I have to use the Gibbs free energy. So if I have to use the Gibbs free energy, what is the relation between the Gibbs free energy density How will I get the Gibbs free energy density in terms of the Helmholtz free energy? Okay. So these are things that you all know, you have forgotten, but that's okay. Uh, Refresh your memory. Just read any simple book. You don't have to read. Who is teaching you StatMed from which book?
So Rajdeep is teaching us from Kardar, and Hyong mostly is following.
Okay, those are Hyphanda stuff. If you want to brush your basics, just take Rife, which is again bedtime storybook, and refresh your memory between what is Gibbs and what is Helmholtz free energy.
Okay, sir.
All right. So, okay. Now, strictly speaking, when you are calculating critical field, you have to always work with Gibbs free energy. This is something I wanted to highlight here, and this is why I have chosen this problem to solve. Let me also admit here something else, that in this case, it would not have made a huge difference. It would not have made a huge difference because if you have a second order phase transition which is going smoothly, then what happens is that close to the critical field, H and B are almost the same. So since H and B are almost the same, you would have gotten here the same answer if you did the whole derivation with the Helmholtz free energy also. But nevertheless, let's proceed with the derivation. Now I have to calculate the total free energy, which is Gibbs free energy. So this is minus d by 2 to d by 2. I am assuming that the center, if this is my film of thickness d, and this is the x-axis, and the origin of the x-axis is at the center of the film. All right. Then the rest of the thing is essentially fairly simple. I'm not writing the limits. So now you can write plus, now you know what the velocity is. Since I am in the London gauge, this velocity is directly given by this, and if I know the velocity, I can get the kinetic energy contribution in the expression for free energy, half mv squared into ns plus, then I will write this in a particular form, not that it has, as I told you here, I could have in principle also used the Helmholtz free energy and gotten the answer, but for the sake of rigor, we are just doing it with the correct free energy. Okay, so this expression BH by 4 pi is what I am writing now in this fashion. So B square by 8 pi anyway was coming directly from the magnetic energy of this Ginzburg-Landau of free energy. The magnetic part of the Ginzburg-Landau of free energy. All right, so good. Now, as I said, I am very close to the critical field. So B is almost equal to H. And I will safely ignore this term. And then the rest I will minimize with respect to psi mod square. So, what will I get? I have these are calculations done in a hurry. Okay. So let me integrate out. Let me do this integral. So since the thickness is so small, there will not be a huge variation of the order parameter along the across the film. So I am just pretending that it's constant. It's not exactly constant, but I don't care. So then I will have, sorry, now I cannot do this. This I am doing something which is too simplified. Let me keep the integral. Okay. Let me keep the integral. You see that these terms here, which I am tick marking, I will just assume them to be constant. So for these, I can write d into this quantity here. But of course, the last term will be different because here I have a x square already. So therefore, when I integrate this, it will become x cubed by 3. And I have a 2 here, so I will get a 6 in the denominator. And what I will get is e squared b cubed h squared by 6 m star c square into psi mod square. Okay, this is e square or e star square. Can someone verify whether I have done it correctly? No, I think it should be should be E or E star. Wait a minute. How did I get E star to E here? Oh yeah, no, that's correct. So this is E star. The limits, remember, were minus d by 2 to d by 2. When I put in the limits and I calculate, here I have replaced E star with twice E. Alright, so this is my Gibbs free energy, and now I will differentiate this Gibbs free energy with respect to psi mod square, and then we can set it to 0. Alright, I can cancel these d's and then this will become d square. So now I have found the solution for psi mod square. So psi mod square will be minus this is minus alpha by beta, that's correct. And then I will have 1 plus E square d square h square by 6 m star alpha c square. Okay, now remember what alpha was. This was, I think, one of the problems that I had told you to solve of what alpha will be. So alpha is minus E star square by m star c square into hc square alpha square. So substitute this here, this instead of this alpha, and you can see what you will get straight away. So this quantity minus alpha by beta is psi infinity square into 1 minus d square h square by 24 h square lambda square. Okay, so now your HC, remember, HC is corresponds to psi mod square equal to 0, and that will immediately give you the expression for HC, so rather HC parallel. So this is HC parallel, which is HC with parallel field. This HC is the regular HC that we had before. This is the thermodynamic HC for the type 1 superconductor. So HC parallel is when this is going to 0, and this will be 2 root 6 HC lambda by D. Okay, so you see, if your D is much smaller than lambda, which you can routinely get in thin films because lambda is often several tens of nanometer, sometimes several hundred nanometer, and we can make routinely thin films which are few nanometer in thickness with a reasonable superconducting transition temperature. So lambda by D can often be very large. It can be 10, it can be 100, and correspondingly HC parallel can be very, very large. This is of course within the ambit of Gainsward lambda. It is here it appears that smaller I make D, larger I can get HC, so I can actually go almost down to one monolayer and get HC parallel to be very, very high compared to the thermodynamic HC. Now that's not correct because at one point you will break the Cooper pair. Cooper pair is something that involves one up and one down spin, and if you apply very large field, then at one point this pairing will get destroyed because you will flip the spins up. It will become two up spins, and two up spins there is not a bound state anymore. So therefore it is this expression has a limit where the microscopic theory will come in and it will no longer hold. Nevertheless, it still tells you that you can go considerably larger than HC and retain superconductivity provided you apply the magnetic field exactly in the plane of the field. You can also write this expression now, write this expression in terms of the HC parallel, and what you see is that it will read like this. Which means that your order parameter is gradually going to 0. Now there is one important thing to note from this. You remember that for a type 1 superconductor, regular bulk type 1 superconductor, in magnetic field at HC, the superconducting transition had become first order. That is no longer the case here. If I have the magnetic field which is parallel to the plane for a thin enough film, then the superconducting order parameter goes continuously to 0. That means that here the transition is second order. Now you can also ask yourself that, okay, the transition is second order for very thin film. So if I start making it thicker, when will the transition from second order will become again first order? Because at some point, if I make it thicker and thicker, I should no longer be in this limit anymore. It will become a bulk sample. And this is your assignment, another assignment. Problem for this week is up to what thickness will the transition remain second order? Okay, good. So we have played enough, I think, with Ginzburg-Landau. From the next class, we'll be into serious stuff. Questions?
Hello, sir.
Yes?
Can you explain again about the stuff you told about the second order transition?
Louder.
This stuff about this second order transition.
Yeah.
Uh, can you explain it again? I did not.
No. So you see, what is a second order phase transition? The second order phase transition is where the order parameter continuously goes to zero.
Yes, sir.
Here you can see that the order parameter is continuously going to zero. It is not having any abrupt jump. So it is h square by hc parallel square. So it is the order parameter psi mod square is reducing continuously, and at hc parallel equal to h, it will become zero. So therefore, here the superconducting transition, the transition from a superconducting state to a normal state, is a second order phase transition. However, if you remember the survey lectures that we did in the beginning of the course, then there we had shown from the thermodynamics of the superconductor, the baby thermodynamics that we did from Rosinus, we have seen that the superconducting transition for a type 1 superconductor in magnetic field becomes a first order phase transition. So what I am telling you is that yes, it is a first order phase transition if you take a bulk superconductor. But if you take a thin film and if you apply magnetic field parallel to the film, then the transition becomes second order. Which means that if now I take this thin film and start making it thicker and thicker, at some point it will no longer remain a film. It will become a bulk sample. And then the transition should switch from second order to first order. The problem is, the assignment problem is to find out at what thickness that happens.
Yes, sir. So for bulk superconductor, the last equation you have wrote is not, valid, right?
Of course, it's not valid.
Okay, sir. So, okay.
Oh, so that gives me an idea of another assignment problem. Okay, we will have another assignment problem on what will happen for a bulk superconductor. That I leave you to derive. It's all variations of this kind of derivation that you will have to do to get all properties of type 1 and type 2 superconductors in magnetic field, except a few microscopic properties that you will not get from Ginzburg-Landau. Any other question? Okay, if not, see you on Friday.
Hello?
Yeah,
Yeah, sir. We see the like oscillation in the TC temperature with H.
yeah,
So there was in the expression there was n minus phi over phi naught.
yes, that's right.
So the phi is H into area. So if someone at a given edge, someone try to change the area of the loop, even then there will be oscillation.
There will be an oscillation. Yes, that is right. But the point is, how do you change the area of a loop? This is a, if you are talking of a physical superconductor, changing the area of the loop is not easy.
Yeah. No, I was just thinking that
Hypothetically,
if
yes, that's correct. It's correct.
that's
Oh. All right. So I will